It turns out that the location of the axis of rotation matters when it comes to moment of inertia. In one case, you could have an axis of rotation that cuts through the middle of a thin rod, and the thing is basically gonna rotate like this so that it is kind of doing this kind of thing. So yeah, a thin rod of length L, let's say, and let's say it's just kind of rotating like this. So that would be a thin rod rotating about its center. And it could have a mass of m. But we could take that same rod and make it so that it rotates about one end instead. In that case, particles have a lot farther to go, some of them. So this would be L from here to here. In this picture, I guess L would be like that. So in other words, this could be thought of as L over 2. So this is a thin rod rotating about one end. Alright, so which one has the higher moment of inertia? We want to use calculus to figure that out. So let's try it. I'll integrate this one first. Axis of rotation is at one end of the thin rod of length L and mass m. So just like any other moment of inertia integration, we want to start with I equals r squared dm. So our typical piece would have a length dl, or perhaps you could call it even dx if you're setting up a x-axis. It would have a mass dm. Alright, now that rod could have a linear mass density. Which would be given by lambda equals the mass of the rod divided by the total length of the rod. Differentiate and find this relationship that dm equals lambda dl. Or you could call it, if you like, lambda dx. And so if we did have an x-axis, we would want to integrate from x equals 0 to x equals big L. X equals 0 to x equals big L. R squared dm. But as usual, we need our dm, our differential, to match the limits. So we'll take our result here, take the lambda dx part, and plug it in. So you'll get I equals an integral from x equals 0 to x equals L of r squared times lambda dx. Now r is going to be the distance from the axis of rotation. That's how it's defined, the shortest distance to the axis of rotation. So this little green piece has a distance of r, but that is also x according to the axis that we set up. So we wouldn't really want to leave it as r. We want to get everything in terms of x. So make that x squared lambda dx. Alright, lambda can come out. X squared has to stay. We can replace lambda with what we know it to be, which is m over L, according to this right here. We could do the antiderivative, which would be x cubed over 3, and we'll go from 0 to L. And let's see what our final results are here. I equals 1/3 ml squared. That's the moment of inertia for a rod rotating around one end. But now we want to try it again with the axis of rotation in a different spot and see if anything changes. Now we want our axis of rotation to be in the middle. And you can take a guess, like if you have the same rod length, where this is L over 2 now, and it has a mass m, same as before, do you think the moment of inertia will be larger than it was here? Or do you think it will be smaller? It's like which object is easier to angularly accelerate? Is it easier to get this one spinning with the same torque as you apply to this one? Or would it be easier to get this one spinning? Take a guess for yourself. And the calculus will tell us it's going to have a mass of dm and we just want to do the same thing as before. We'll say that the total moment of inertia will be an integral of r squared dm. Let's give it limits now. We could set up an x-axis, but this time we'll be integrating from a x of negative L over 2 to x of L over 2. So let's put those in as our limits. But remember, these are x values. Okay, our r squared. R can be replaced with x because the distance from center to any given piece would be a distance r, which is also x. We would have a negative, I guess, if we went backward, like to a piece that was over here. But we're going to be squaring that anyway, so it won't matter. So r would be, I guess, negative x here. So you could always say that r is the absolute value of x, is the idea. Alright, so we have absolute value of x squared, but I don't have to put that in, just x squared will suffice. When it comes to dm, we have the relationship lambda equals m over L, so that's dm over dl. Therefore, dm is lambda dl. Put that in. But we want to get everything in terms of a single variable, so let's replace the dl with dx. And let's see what the results of this integration will be. Alright, so pull the lambda out front. Alright, so the antiderivative there will be x cubed over 3 from negative L over 2 to L over 2. Our lambda can be replaced by m over L. And we just want to plug in I'll pull the 1/3 out. It leaves behind L cubed over 8 plus L cubed over 8. Which is basically 2L cubed over 8, which is L cubed over 4. Therefore, the moment of inertia of this rod would be 1/12 ml squared. So, is it greater moment of inertia or less? It is less. Because a lot of the mass here is concentrated near the center axis. Here, a lot of the mass is concentrated really far from the axis. And that's the point, is even though these objects are the same shape, the placement of the axis of rotation matters. This one has the lower moment of inertia. And this one has the higher moment of inertia. Alright, so what's the results? This one's easier to angularly accelerate. This one's harder to angularly accelerate.